Hello everyone. This is the first of two tutorials on orienting an object towards another in Unity. Specifically, we will see how to make the 3D model of a surveillance camera automatically orient itself towards the player, following their movements within the scene. This tutorial was created using Unity 2022 and is divided into two parts. In the first part, we will analyze the problem and approach it using the rotate method to achieve an instant rotation of the camera. In the second part, we will use quaternions and the slurp method to create smoother and more gradual rotations. Before we go on, I remind you that, as it happens with most of my tutorials, the text version of this video tutorial is available for free download at the link provided in the description. Let's analyze the problem to be solved before moving on to the implementation. The camera can only rotate around its local vertical axis, so we can reduce the problem to the 2D plane. To make this aspect more understandable, I am framing the scene from the top viewpoint in orthogonal mode. Both the 3D model of the surveillance camera and the player have, like all game objects, XYZ position coordinates that identify their position in the scene. We are not interested in the position.y coordinate because the camera can only rotate around that local axis, so we will only consider the x and z position coordinates, as if the two objects were on the same plane, with the same value for their y coordinates. In our case, moreover, the surveillance camera can be considered as the origin of the reference system, what would be the origin in a Cartesian plane at point 0, 0. Not only that, but we can also consider the direction framed by the camera, which in this case corresponds to the negative local y-axis, as one of the Cartesian axes. We can then identify the direction that connects the virtual camera and the player's position in the scene. This is simply a vector, which in this case we will also consider only in two dimensions, i.e. global x and z. It follows, therefore, that the rotation we want to apply to the surveillance camera is given by the angle that separates the asset's orientation, its negative local y-axis, and the ideal vector connecting the surveillance camera to the player. By finding this angle, we will have the rotation to be applied to the 3D model around its local vertical axis. We are very lucky. There is a mathematical function called the two-argument arctangent, implemented by the A102 method in MathF, which calculates precisely this angle by taking, as a parameter, the direction vector, given by the difference between the coordinates of the 2 points. Specifically, A102 considers the angle between the x-axis of the Cartesian plane and the direction vector between the origin and the target. In our case, the origin is given by the x and z coordinates of the 3D model of the surveillance camera, so the target coordinates, x, y, will be given by the difference in coordinates between the surveillance camera and the player, while the x-axis coincides with the negative local y-axis of the surveillance camera. The function takes two parameters in reverse order. In the Cartesian plane, in fact, we have A102yx. In our case, considering Unity's reference system, where the x-axis is the lateral one, the z-axis is the frontal one, and the y-axis is the vertical one, which we do not consider here, we will write A102xz. Unity's online documentation tells us that mathf.a102 takes the y and x coordinates, which in our case will be x and z, and returns as a float value the angle in radians whose tangent is y divided by x. The rotate function in Unity wants a rotation angle in degrees, so we will have to take into account this difference in units of measurement and the necessary conversion when writing the code. Now that we have analyzed the problem and its solution, let's move on to the first implementation, instant rotation with rotate. First, I create a new C# script called lookat object. to be associated with the actual surveillance camera. I say actual surveillance camera because this asset is actually composed of three elements: a base to be placed on the wall, a pivot element, and the camera. We are interested in having the camera rotate around its vertical axis, i.e., around its local vertical axis. In Unity's virtual universe, the global vertical axis is the y-axis, but each object can have its own local reference system. In the case of the 3D model of the surveillance camera, this is the local z-axis, as we can see by switching to local display mode in the Unity editor. This distinction introduces a slight complexity into our project. We will need to calculate the rotation angle on the global plane of the scene, using the x and z coordinates of the objects, and then we will need to perform the rotation around the local vertical axis of the asset. First, let's create a reference to the object to follow by creating a transform variable called object A, which we associate with the player in the inspector. Having done this, we can move directly to update to implement the solution discussed earlier. I remind you that the local vertical axis of the camera is its z-axis. We need just 3 lines of code. In the first, we will calculate the angle that separates the camera's current orientation from the one it should have to point at the object. In the second, we will calculate the amount of rotation to be performed around the camera's local z-axis to achieve the desired orientation. In the third, we will perform the actual rotation with the rotate method, to which we will need to give 2 parameters: the local vertical vector and the amount of rotation to be performed around that vector. Let's start with calculating the angle between the surveillance camera's orientation and the one it should have, using mathf a102 function, which returns a value in radians that we will convert to degrees. We have seen that in the 2D plane, a102 takes 2 parameters: the difference between the y-coordinates and the difference between the x-coordinates of the 2 points, target and observer, in this order. In our scenario, with Unity's global coordinate system, where x and z are on the 2D plane, while global y identifies the vertical axis of the scene, we will need to write float theta equals mathf a102 object a.transform.position.x minus transform.position.x, object a.transform.position.z minus transform.position.z. But we are not done yet. In the same instruction, add at the end mathf.red to deg to convert the result to degrees. Having done that, we can move on to the second instruction, calculating the rotation to be performed in degrees, which can be easily done with float delta angle equals mathf.delta angle transform.eulerangles.z theta, where transform.eulerangles.z represents the current orientation of the surveillance camera, while theta represents the orientation, calculated in the previous step, that it must assume. The third and final instruction allows us to rotate the surveillance camera. Transform.rotate vector3.forward delta angle. Note that I used vector3.forward, which identifies the local z-axis of the object as the vector around which to perform the rotation. This is due to the fact that, in the specific case of this 3D model, The local z-axis is not the one that indicates the front and back, but the local vertical axis of the object. Save the script, switch to the Unity editor, and press play to evaluate the final result. Note: if you notice that the surveillance camera is not pointing towards the target, make sure that the initial XYZ rotation values of the surveillance camera is set to 0 in the inspector and try again. So, to recap, in this first part we examined the problem to be solved and saw how to consider the two objects on the same plane, how to calculate the direction vector, and, most importantly, how to apply it to the specific case of the surveillance camera, taking into account its local reference system. We then applied an instant rotation to the object, making it point at the player at every frame of the game, using the rotate function. In the next part, we will see how to calculate the rotation quaternions and use the SLERP function to rotate the object more slowly. See you soon!